Hey guys, welcome to the homework help tutorial for Chapter 2, Unit 5, Graphs and Exponential Functions. So here's 5.2. So for the first one, guys, you just need to vocab. You guys can knock that out. The first set that we have here, it's asking us to write a function that represents each population as a function of time. Now, in class, we covered uh, our function, our population function, as P of t is equal to P naught times the quantity of 1 plus r to the t power, and again, t being time. So number 1 is kind of done for us. So let's take a look at number 2. Youngstown has a population of 12,000. Its population is increasing at a rate of 1.2%. So there's a few things we have to do. First things first, we have to get our P naught, or our initial population. That would be 12,000. So that's given to us right here. The second thing we want is our rate. Our rate is given to us right there. But remember, every time we write our rate, we have to write in decimal. So that's 0.012. If you're not quite sure, remember how to write the decimal. It's just 1.2 and divide that by 100. When you do so, you get 0.012. So now that we have our initial value, an initial population, and our rate, then we can substitute our values in here to write a function. So it would be P of t is equal to our initial population, 12,000, times the quantity of 1 plus 0.012 to the t power. This is in parentheses, so we can actually add this and reduce or simplify this just a little bit further. We get 12,000 times the quantity of 1.012 to the power of t. And this is the function that we're looking for. So it's just that easy, guys. We've given you one example up here, and now you have a second example here. Remember, you can always pause and forward as needed. So I'm going to scroll down to look at a second set, and pretty much 1 through 6 are all the same. So in 7, now that we have our function, we're given a t value or time value, and we're asked to find our ending population. So Waynesburg has a population of 16,000 to begin with. Its population is increasing, so we know it's an exponential function increasing at a rate, and remember, the word increasing means that we are adding, at a rate of 1.5%. The function, so they're giving us the function, is given there, represents the population as a function of time. Determine the population after each given number of years. Round your answer to the nearest whole number. So for number 7, they're giving you an example, and I'm just going to show you what number 8 would look like if we go step by step. So they're giving us t is equal to 3 years, which means we can write that down. We know that our population, or our function, is given to us by P of t is equal to 16,000 times the quantity of 1.015 to the t power. And I grabbed this function from here. That's where this came from. They're giving it to us. So, which means that if we know what t is, all we have to do is plug it in, and we're pretty much done. Our second line can be written as follows: 16,000 times the quantity of 1.015, and instead of t, we're going to substitute that value because we know that t is equal to 3 for 3. You can then use your calculators, guys. So let me just show you what that would look like. Here's my calculator. Turn it on, clear. So we get 16,000 times the quantity, so I open my parentheses, of 1.015, close parentheses, to the power of 3. And that's our answer. So let me just kind of blow that up a little bit so you guys can take a look. And there's our answer. So we end up getting that our total population, or our ending population, is P of t is equal to, let me bring that screen back up, 16,730. 16,730. And we can add a couple decimal places. But since we're talking about people, I mean, you can't really find a 0.85 person. So let's go ahead and just round to the nearest whole person, which would make this a 1. So let's switch this out to 1. 1. That's how many people um, Waynesburg will have after 3 years. So now let's take a look at a separate or a different set. Now that we know the years, we're going to go to our other set. Is they're giving us our final population, and we have to determine how long it would take us to get to that population. So Morristown has a population of 18,000. Its population is increasing at 1.2%. The function, so they're giving us what the function is, represents the population as a function of time. Use the graphing calculators to estimate the number of years it will take for the population to reach this given amount. So 17 to give you an example, but let's do 14 together so you can see where this comes from. Now, we want to find out what years are, so we don't know what t is. T, we don't know. We need to figure that out. So let's plug everything in and see what we can come up with. We know we're using this function, and we know we have to get at this population. So there's two things we're going to graph. Our function, which is just 18,000 times the quantity of 0.988 to the t power, and we know that our final population, which can be written as y equals, or p of t is equal to, is 15,000. If we punch that into our calculator, we're able to find an intercepting point, and this will give us the value that we're looking for. So let's go to our graph functions. Let me see if I can bring up that other window. Let me bring it down here. So I'm gonna delete what I have up here. Okay, let's put in our function 1800,000. There you go. Times the quantity of 0.988, which is the function that was given to us, correct? To the power. And again, our calculator doesn't have the t, since we are doing y and x for our Cartesian plane. We're going to use the variable x. For our second row, we're going to write down what we want our population to be. That's 15,000. Just to make sure that our graph intercepts, let's change the window. Let's scroll down to y max, and let's change our window to something close to 15,000, so maybe 16,000. And let's change our scale to be by the thousands. It's fine. If we graph, we should come up with something very nice graph. I was plotting data points earlier. So I'll delete this in a second. What we really want is that blue and red line. So let me go up here, delete my plot. We don't really need that. All we want are two solid lines. There's the blue one, and there's our red one. So to find that intercepting point, we just go second, calc. Remember, we want intersecting points. Enter. It asks us for our first curve. That's our first curve. That's our second curve. And then we can just make an initial guess somewhere around there. And the calculator will pinpoint exactly what that intercepting point is, which means at 15,000, which is our red line, it's going to take us 15.1 years. So let's approximate that. We can keep it at 15 years. So it will take us, we can write, about 15 years to have 15,000 people. And that becomes our answer. So again, for these guys, feel free to pause, go back as needed, and take thorough notes. This will help you guys out in your homework and ultimately in your quizzes, mastery quizzes, and ultimately on your final exams. So let's move to the next set. So then in 19, we're asked to now complete the graphs or just to graph. I believe I gave you guys a couple of these. So there's an example of one, number 19. And if you look at the notes for lesson 2, the graphing ones, I kind of walk you guys through this process. So let's take another look at this one. So for number 20, and again, as stated before, we look at the function f of x is equal to 4 to the x power. If we compare that to our parent function, f of x is equal to ab to the x power, there's a few comparisons that we can make. This x is an x, and this b would be our value of 4, and right in front we have times 1. So if we were to write these down, we have that a is equal to 1 and b is equal to 4. Well, our rule said that if b is greater than 1, we automatically know that this thing is increasing. So we are increasing. It's an increasing function, which means it's going to look something like that, exponential function. So now let's fill up the rest of this table and see what that looks like. Again, you can use the calculator for this, or you can do it by hand, entirely up to you. I'm okay with either way. Let's go back to our home. Let me see if I can bring up the other screen. So we have negative 2, we have 4 to the power of, and then we plot in our values, negative 2. Well, that gives us let's write that 0.0625, 0.625. The next one, we can use that copy-paste feature that I spoke about in the other video notes. So we can go second, enter, and just change the top value to a 1, and then enter. We get 0.25, which is a quarter. We go to 0, we're going to get 1, because a number to the power of 0 is 1. Any number to the power of 0 is 1. If we go 4 to the first power, we get a 4. And if we get 4 to the second power, we get 16. So there we go. We have our ordered pairs. Now it's time for the easy part. Negative 2 and 0.606. So that's very, very, very close to 1. So I'm just going to put 0.06. This is going to be negative 1, 0.25. This is 0 and 1, 1 and 4, 2 and 16. So we have a bunch of points. Let's go with negative 2. Negative 2 would be here. Notice how our graphs are going by negative 2, 4, 6, 8, so on, so on, so on all directions. So this would be negative 2. And we would only go about yay high because it's very close to 1. Negative 1, somewhere in the middle here, and that's a quarter, so that just goes just a slight tad higher. And if you're not that accurate, it's fine, as long as you can approximate or get a visual. 0 is close to, 0 is at 1, so we'll say 1 is around there. Let me kind of clear some of these up a little bit. Remember, it gets very, very close to 1, 0, but never touches. And then 1, 4. So here's 1 and then 4. And then 2 and 16. That's 2 and 16. So our graph is going to be very, very steep. It goes in, it touches here, it gets very, very, very close, but never ever touches. And that's what our graph would look like. There's a few things that were asked of us. Our asymptote is going to be at y is equal to 0. So that's our y asymptote again, our horizontal, so 0. I believe they wanted to know that. Yeah. So we can write asymptote is equal as y equals 0. This function is increasing as we stated before. Our y int is at 0, 1. Our domain is all real numbers, and our range is everything greater than 0. That's it. Let's see if there's one more type of problem. That appears to be it all for 5.2. So again, guys, if you practice one of these, you can pretty much knock out the rest, and this is very good practice for your mastery quizzes and everything else we're doing in class. Hope this helped, guys. I'll be posting up the homework review for 5.3 shortly. See ya.